What if humanity isn't standing at the beginning of discovery, but at the edge of confirmation? For decades, scientists have asked if life exists beyond Earth, scanning the skies for signals, searching distant planets for the faintest clue. But what if the first undeniable sign has already been found, and most of the world barely noticed? Tucked away in data from the James Webb Space Telescope, the discovery emerged that stunned even the most skeptical researchers. A faint chemical fingerprint appeared on a planet over 120 light-years away, buried in the glow of its star, so subtle it could easily have been dismissed. But it wasn't dismissed, because what they detected isn't just any molecule. On Earth, it's only made by light. No volcanoes, no storms, no chemical tricks can produce it in meaningful amounts. And yet, there it was, floating in the skies of a faraway world, like a message written across the star. Imagine what this means. For generations, the question, "Are we alone?" has been treated like philosophy, like speculation. But now it's shifting into something else, something closer to fact. The planet in question, a massive ocean world called K218b, doesn't just harbour strange chemistry. It carries signs of stability, warmth and oceans that could have endured for billions of years. In other words, the perfect stage for life. Not just microbial, but possibly something far greater. And here's the part no one wants to admit. If life is there, intelligent beings may already know we exist. The radio waves we've been sending into the void for a century have only just reached their skies. And the thought that someone somewhere might already be listening, that's not science fiction anymore. That's reality pressing in on us. Undeniable and impossible to ignore. It started quietly, the way most history-changing discoveries do. The dataset, a series of spectral lines, a faint chemical whisper hidden in the light of a distant star. No thunderclap announcement, no grand revelation, just numbers and curves plotted on a graph by scientists who had been staring into the void for years, almost used to disappoint. Yet in September of 2023, as researchers combed through information gathered by the James Webb Space Telescope, something caught their attention that refused to go away. The planet under observation was one already known to astronomers, orbiting a dim red dwarf in the constellation Leo. It was classified as a sub-Neptune, a world bigger than Earth but smaller than Uranus, enveloped in a thick atmosphere that made it hard to imagine any kind of familiar life thriving there. Still, it was intriguing because it orbited within the star's habitable zone, that delicate band of distance where temperatures might allow liquid water to exist. And as every astronomer knows, where there is water, there is potential. But this time what they found wasn't just water. The data revealed the presence of a molecule so improbable, so biologically suggestive, that even the most cautious scientists felt their hearts race. Dimethyl sulfide, DMS for short. On Earth, this compound is produced exclusively by life, primarily by phytoplankton drifting through our oceans. It is quite literally the smell of the sea, the invisible fingerprint of biology at work. Volcanoes don't make it. Chemical reactions in the atmosphere don't churn it out. Lightning storms, comets, cosmic radiation, none of them can account for it. If you find DMS, you're looking at biology, plain and simple. And here it was, floating in the skies of a planet 120 light-years away. The significance hit hard. It wasn't just another exoplanet with water vapor or methane, things that can appear through purely geological processes. This was different. This was the kind of evidence scientists had always dreamed about, but never expected to see so clearly. Skepticism kicked in immediately, as it always does. Could it be an error in the telescope's instruments? A quirk of calibration? The Webb telescope is precise beyond belief, capable of splitting light into its component colors to detect molecules in distant atmospheres. But it is also new, and scientists know the dangers of confirmation bias, so the team did what scientists do best. They checked, rechecked, and tried to poke holes in the data. The DMS signature wasn't strong, not yet overwhelming, but it was there with enough confidence to merit attention. Combined with other atmospheric readings, it painted a picture that was hard to dismiss. K218b's skies revealed not only dimethyl sulfide, but methane and carbon dioxide, two gases that, when found together, raise eyebrows. Methane is unstable. It breaks down under stellar radiation, unless something replenishes it. On Earth, that something is biology. Volcanoes can produce methane, but not at the levels suggested here, and not with the accompanying cocktail of gases. What was even stranger was what scientists didn't find. Ammonia was conspicuously absent. In a lifeless hydrogen-rich atmosphere like K218b's, ammonia should dominate. Its absence was a riddle, one that suggested the planet's chemistry was being altered by active processes suspiciously like the kind we associate with life. At this point, the discovery began to ripple outward, from research circles into the public sphere. Headlines blared. Signs of life on exoplanet? Alien oceans may harbor biology. Yet the scientists involved were careful, cautious to a fault. They refused to call it proof, because proof is a dangerous word in science. Instead, they called it evidence, the strongest yet, but still requiring more observations, more confirmation. Yet even their caution could not mask the implications. For decades, the hunt for life had focused on the faintest traces, water molecules, potential habitable zones, atmospheres with suggestive gases. Now, suddenly, the game had shifted. Here was a specific biological marker, one that on Earth is inseparable from life, detected light years away. It was no longer just maybe or someday. It was here now, in the data. To grasp the enormity of this, you have to understand the odds. The James Webb Space Telescope is peering across staggering distances, pulling faint starlight apart to analyze the way it filters through a planet's atmosphere. Imagine looking at a candle flame through a fogged window from miles away and being able to tell not only that the flame is burning, but what the air around it is made of. That's the scale of precision involved. For Webb to detect dimethyl sulfide at all suggests it's present in significant quantities, produced continuously on that planet, the way Earth's oceans constantly release it into our skies. The possibility that K218b is a living world isn't just speculation, it's a hypothesis backed by data, and one that cannot be dismissed out of hand. For the scientific community, it was a moment of reckoning. If this was real, if the signal held up under future scrutiny, then humanity had stumbled across something monumental, the first chemical proof that we are not alone, not intelligent aliens, not flying saucers in the sky, but something deeper, life in any form, thriving beyond Earth. Microbial or complex, simple or bizarre, it didn't matter. The discovery would redefine humanity's place in the universe. We would no longer be the singular miracle we believed ourselves to be, but part of a vast cosmic tapestry where life is not an anomaly, but a rule. For the public, the story sparked fascination and fear in equal measure. People wondered, if life exists there, how advanced might it be? Could it be intelligent? Could they be watching us as we are now watching them? After all, Earth has been leaking radio signals into space for over a century. Those signals, traveling at the speed of light, have now reached the distance of K218b. If intelligent beings live there, they may already know we exist. The thought is electrifying and terrifying. For the first time, the question of are we alone no longer feels like science fiction. It feels like a headline waiting to break. But scientists urge caution. They remind us that extraordinary claims require extraordinary evidence. A faint chemical signature is not yet a smoking gun. More observations are planned, using Webb and other instruments, to confirm or refute the findings. The debate rages on in scientific journals, with some urging restraint, others daring to hope that we've just glimpsed the first proof of alien biology. Yet even the skeptics admit something unusual is happening on K218b, something that defies easy explanation, and that alone makes it one of the most tantalizing worlds in the cosmos. Still, whether the signal proves to be the final proof or just another step in the search, its impact is undeniable. Humanity has crossed a threshold. We're no longer asking only if life could exist out there. We're asking where it already exists, and what form it takes. The discovery of dimethyl sulfide on K218b may turn out to be a footnote in the history of science, or it may be the first chapter in a story that changes everything. Either way, the universe feels different now, more alive, more mysterious, and much closer to us than we ever dared to imagine. To understand why the discovery on K218b is so electrifying, we first have to grasp what kind of planet we're dealing with. This isn't a second Earth, not by a long shot. It's bigger, heavier, stranger, and in many ways far less forgiving, classified as a sub-Neptune. K218b sits in a category of planets that we don't even have in our own solar system. It's about 8.6 times the mass of Earth, and more than twice its radius. placing it squarely between the rocky worlds we're familiar with and the gas giants like Uranus or Neptune. That already makes it fascinating, because it challenges our assumptions about habitability. For decades, scientists imagined the search for life would be about finding Earth 2.0, rocky planets with breathable air, oceans of liquid water, and climates not too different from our own. But K218b throws that assumption out the window. It shows us that life might thrive on worlds utterly alien to our expectation. Orbiting a small red dwarf star about 120 light-years away, K218b sits in the so-called habitable zone, the distance where liquid water could exist. But here's the twist. The conditions on its surface, if you can even call it a surface, are unlike anything on Earth. Instead of an atmosphere dominated by nitrogen and oxygen, this world appears to be wrapped in a hydrogen-rich envelope, something more akin to the upper layers of Neptune. That hydrogen blanket gives the planet a kind of otherworldly character, lighter gases floating high, trapping heat, creating pressure and temperatures that seem impossible to reconcile with life as we know it. And yet, that's exactly where the evidence points. Deep beneath that thick atmosphere, scientists believe, may lie vast oceans, not shallow seas like the Atlantic or Pacific, but colossal hydrogen water oceans stretching hundreds of miles deep. Imagine an entire world dominated by an endless, crushing sea, its waves rolling beneath a permanent blanket of cloud. That's the image researchers conjure when they describe K218b as a Hycean world, a new class of planet only recently theorized. The term comes from hydrogen and ocean, a combination once thought too extreme for life, but now emerging as one of the most promising environments in the galaxy. On Earth, oceans teem with life, even in the harshest places at volcanic vents, in acidic depths, under ice sheet. If life can thrive here, why not in oceans unimaginably larger and older, sheltered by a hydrogen-rich atmosphere that could keep them stable for billions, even trillions of years? The stability of such an environment is one of its most compelling features. Red dwarf stars, though small and dim, burn their fuel with extraordinary efficiency. While our sun will live about 10 billion years in total, red dwarfs can shine steadily for tens of trillions of years. That means planets like K218b could remain habitable far longer than Earth, offering a stage for life not just to emerge but to evolve into something complex, enduring and unimaginably diverse. If Earth has managed to produce intelligent life in just a few billion years, imagine what could happen on a planet with a lifespan many times longer. K218b doesn't just suggest life is possible, it suggests it might be inevitable. The most unsettling part, however, is how Earth-like its climate appears to be, at least in one crucial respect. Despite its alien nature, K218b's equilibrium temperature hovers around 120 degrees Fahrenheit. For human beings, that might sound uncomfortably hot, like the deadliest summer days on Earth. But for biochemistry, it's close to perfect. That exact range is where many chemical reactions necessary for life can occur efficiently, where water remains liquid, and where molecules can bond, split, and reorganize into the building blocks of biology. It's not too hot to boil everything away, not too cold to freeze everything solid. It's a cosmic sweet spot. And what makes it even more mysterious is that K218b isn't alone in hitting that target. Other exoplanets flagged as potentially habitable also seem to hover near this same range, as though nature is pointing to 120 Bifefibis as the golden zone for life. Coincidence? Maybe. Or maybe we're starting to glimpse a universal pattern. Yet with all this promise comes a daunting sense of alienness. Gravity on K218b would be at least twice as strong as on Earth, maybe more, pressing down with a force that would make human exploration nearly impossible. The hydrogen-rich atmosphere would be utterly toxic to us, incapable of supporting oxygen-breathing organisms like ourselves. Even the light from its star would feel strange, red and dim compared to the golden warmth of our sun. If you stood on some floating platform in its skies, the world around you would look utterly alien, an endless ocean below, thick clouds above, the faint reddish glow of its dwarf star painting everything in hues we can barely imagine. And yet, despite this alienness, the planet may be alive, not just alive in the microbial sense, but alive in a way that redefines what habitable even means. This is why the dimethyl sulfide discovery was such a shock. If life is producing that molecule, then it's doing so in an environment completely unlike Earth's. under conditions once thought inhospitable. That alone shatters our narrow view of habitability. It suggests that life is far more flexible than we ever imagined, capable of adapting to atmospheres rich in hydrogen, to oceans hundreds of miles deep, to gravities that would crush us flat. It expands the playing field from Earth-like planets to an entire class of worlds we hadn't even considered viable a few decades ago. Suddenly, instead of a handful of possible life-supporting exoplanets, we're looking at hundreds, maybe thousands. The galaxy doesn't just hold the occasional oasis, it may be full of them waiting for us to discover, and this raises a haunting possibility. If K218b has remained stable for billions of years, and if its oceans are as vast and enduring as models suggest, then life there may not be in its infancy. It may be ancient, older than us, more evolved, more diverse, maybe even more advanced. While Earth has hosted complex life for only 500 million years, K218b may have had 10 times that span to let evolution run wild. What forms could emerge in oceans hundreds of miles deep, untouched by extinction events, unbroken by catastrophic climate shifts? Would they be microbial, massive, or intelligent in ways we can't begin to comprehend? These are the questions scientists dare not voice too loudly, for fear of sounding too speculative. But the evidence whispers them all the same. For now we know little. We don't know if K218b has continents or only ocean. We don't know how its chemistry interacts with its atmosphere, or what its clouds are truly made of. We don't know if the dimethyl sulfide is real, or if it's some strange chemical quirk we've misunderstood. But what we do know is this. K218b challenges everything we thought we knew about habitability. It isn't Earth-like, and yet it may be far more habitable than we ever dared to imagine. It stands as proof that life may not need an Earth clone to emerge. It may thrive in worlds utterly alien to us, under skies we couldn't breathe, in oceans we couldn't survive, orbiting stars we barely notice in our night sky. And if that's true, then the search for life just exploded in scale. Because K218b is only one of thousands, and if life can exist there, then it may exist everywhere. When scientists talk about oceans, we instinctively imagine something familiar. The rolling blue expanses of Earth, sunlight filtering through waves, coral reefs teeming with fish. But the oceans suspected on K218b are nothing like that. They are deeper, darker, stranger, vast bodies of water hidden beneath thick blankets of hydrogen, stretching not for miles, but for hundreds of miles into the planet's depths. These are not seas as we know them, but alien abysses, colossal aquatic worlds, whose scale makes our Pacific Ocean look like a shallow pond. To imagine what life might look like there, you have to abandon almost everything you know about Earth and think in terms of extreme. Models suggest that beneath K218b's thick hydrogen-rich atmosphere lies a liquid ocean, formed as pressure and temperature combine to keep water stable. But unlike Earth, where oceans interact constantly with the land and sky, exchanging gases and nutrients, K218b's oceans may be sealed worlds. They could be capped by dense clouds and blanketed with hydrogen, isolating them from the kind of cycles we rely on for life. At first glance, that sounds hostile, a suffocating prison where nothing could thrive. But on closer inspection, it's possible that this stability is what makes them ideal. Shielded from cosmic radiation, meteor impacts, and violent weather changes, these oceans could remain unchanged for billions, even trillions of years. On Earth, life has survived repeated extinctions, ice ages, and asteroid strikes. On K218b, the environment may have been steady enough to allow life to flourish uninterrupted since its beginning. Consider what we know of life in Earth's own extreme oceans. In the crushing blackness at the bottom of our seas, where no sunlight penetrates and pressure would kill unprotected humans instantly, life not only exists but thrives. Entire ecosystems bloom around hydrothermal vents, with strange creatures feeding on chemical energy instead of sunlight. Giant tube worms, ghostly white crabs, translucent fish, all thriving where temperatures swing from near freezing to hundreds of degrees in the space of a few feet. If life can flourish in such extremes here, why not on K218b, where oceans may provide chemical gradients and energy sources on planetary scale? Some scientists speculate that the chemistry of those oceans could be radically different from ours. With hydrogen dominating the atmosphere, Life might rely on biochemistry unfamiliar to us, perhaps hydrogen-based instead of oxygen-based. Instead of breathing oxygen, organisms could consume hydrogen or methane, using energy cycles completely alien to Earth. And if that's the case, then these oceans may host forms of life we wouldn't even recognize at first glance, beings that don't fit our definition of biology but are alive all the same. Imagine creatures that drift through endless waters, fueled not by sunlight but by exotic chemistry, glowing with their own bioluminescence in the eternal dark. Entire ecosystems could exist beyond our comprehension, adapted to oceans deeper than the tallest mountains on Earth. The scale itself is mind-boggling. Earth's deepest point, the Mariana Trench, reaches just under 7 miles. On K218b, oceans might plunge hundreds of miles deep, with pressures so immense they could crush steel. Yet such depths may also provide layers of habitability. Near the upper levels, where temperatures and pressures are more forgiving, microbial life could flourish, producing gases that rise into the atmosphere, perhaps even the dimethyl sulfide we've already detected. Deeper down, larger organisms might roam, evolved to withstand unimaginable pressure, their bodies shaped by physics we can barely simulate. We might never know them directly, but their presence could leave signatures detectable from light years away. This leads to one of the most haunting aspects of K218b's oceans, their potential to host not just simple microbes, but complex evolving ecosystems. On Earth, life remained microbial for billions of years, until conditions stabilized enough to allow multicellular organisms to appear. If K218b's oceans have been stable far longer, the leap to complexity may have happened long ago. What might evolution produce in an environment so vast, so constant, so alien? Could there be creatures larger than whales drifting through those waters, sustained by chemical energy? Could intelligence arise in such an environment? Beings who know only the endless ocean, never seeing stars, never walking on land, but developing their own forms of communication and society in the deep. It is speculation, but speculation that flows naturally from the conditions we see. Even more intriguing is how these oceans interact with the planet's atmosphere. On Earth, our oceans act as regulators, absorbing carbon dioxide, releasing oxygen, shaping our climate. On K218b, the chemistry would be different, but the principle may be the same. If microbes or other organisms thrive in the upper oceans, their activity could shape the atmosphere in detectable ways, explaining the strange absence of ammonia and the unexpected abundance of methane. In other words, the oceans may be alive, not just with creatures but with processes that reach into the skies and announce themselves across space. The very signal we've detected, the fingerprint of dimethyl sulfide, may be the echo of life in those alien waters, carried on winds we can barely imagine. There is also the eerie possibility that these oceans are not entirely liquid. At certain depths, pressure could turn water into exotic forms of ice, Ice 7 or Ice X, solids that remain frozen even at temperatures far above Earth's boiling point. Beneath the oceans, a mantle of high-pressure ice could separate the water from the rocky core, creating a strange sandwich of ocean and frozen rock. If that's the case, then life would be confined to the upper layers, never reaching the minerals and nutrients of the planet's crust. Yet, even that confinement might not stop it. On Earth, life thrives in places completely cut off from sunlight and geology, surviving on nothing but chemistry. On K218b, similar processes could sustain oceans teeming with life, floating atop a frozen abyss. The sheer strangeness of these oceans forces us to confront a larger truth. We have no idea how diverse life can be. For centuries, we assumed life required Earth-like conditions. Then we discovered extremophiles, organisms that survive in acid in boiling springs, in radioactive waste, in the vacuum of space. Each discovery has expanded the boundaries of possibility. K218b represents the next step in that expansion, a reminder that life is not fragile but adaptable, not rare but resilient. If life can find a foothold in such oceans, then it can find it almost anywhere. But perhaps the most chilling thought is this. What if those oceans are not just habitats but cradles of civilizations? Intelligent beings could evolve in endless seas, their societies shaped by currents and pressure instead of fire and land. They might build no cities, no monuments, nothing we would recognize, but their intelligence could be expressed in ways alien to us, through sound, through light, through collective behavior. If such beings exist, They may never leave their oceans, never see the star, and yet, ironically, we may detect them before they ever know we exist, reading the chemical whispers of their world while they remain unaware of ours. K218b's oceans are more than an exotic curiosity. They are a possibility, a test case, a glimpse into a universe where habitability takes countless forms. Whether they hold microbes or monsters, they remind us that life is not an earthbound phenomenon, but a cosmic one. And the deeper we look into their dark, crushing waters, the more we may find ourselves staring into a mirror, not of our world as it is, but of what life can be when the universe is given the freedom to experiment endlessly. When scientists first began studying K218b's atmosphere, they expected to find something chaotic but explainable, a cocktail of gases produced by geological processes, chemical interactions, or the random quirks of a sub-Neptune world. After all, planets wrapped in thick hydrogen-rich atmospheres are supposed to be predictable. You model the physics, you calculate the chemistry, and you get a fairly consistent result. But what the James Webb Space Telescope revealed about this planet was not just unexpected, it was downright unsettling. The data didn't fit the models. The atmosphere wasn't behaving the way a lifeless planet should. And in science, when the equations don't add up, it means there's something we're not seeing. Let's start with the basics. A hydrogen-rich atmosphere, especially on a world of K218b's size, should be full of ammonia. On Earth, ammonia is a minor trace gas, quickly broken down by sunlight. But on a planet like this, with deep oceans and a hydrogen-heavy atmosphere, ammonia should accumulate in large quantities, becoming a dominant feature. Yet when Webb's instruments analyzed the starlight filtering through K218b's skies, ammonia was conspicuously absent. That alone raised eyebrows. It wasn't just low, it was missing in amounts that defied expectation. Something, it seemed, was actively removing it, or preventing it from forming in the first place. In its place, scientists detected methane and carbon dioxide, two gases that tell a very different story. Methane is tricky. It can be produced geologically, yes, but it doesn't last. Ultraviolet radiation from the star should break it down quickly. On a planet bathed in stellar light, methane should disappear unless it is constantly replenished. On Earth, biology does that job. Microbes, wetlands, and even livestock produce methane in vast quantities, keeping our atmosphere supplied despite the sun's relentless breakdown. To see methane on K218b in such abundance means one of two things. Either there's some unusual, unknown geological process at work, or something alive is producing it. Neither explanation is easy to swallow, but both suggest something out of the ordinary is happening. Then there's the carbon dioxide. At first, CO2 might not seem surprising. It's one of the most common gases in the universe, but its presence alongside methane is what makes scientists pause. The two gases don't like to coexist for long. Chemically, they should interact, reducing one another over time. If you find both together in significant amounts, it suggests an active ongoing process maintaining the balance. On Earth, that process is life. Plants and microbes producing oxygen and methane, balancing out the chemistry of the atmosphere in a way that would collapse without biology. To see a similar dance of gases on K218b is, to put it mildly, suspicious. And then comes the real kicker, the faint but tantalizing detection of dimethyl sulfide. As I described before, DMS is a molecule produced on Earth only by life, mostly by phytoplankton in the oceans. To see even a hint of it in the atmosphere of K218b is astonishing. Combined with the absence of ammonia, the presence of methane, and the coexistence of carbon dioxide, it creates a picture that no simple geological model can easily explain. It's as though the planet is whispering, in chemical language, that something unusual is happening beneath its clouds. Now, skeptics are quick to point out that we must be cautious. Our instruments, as advanced as they are still straining against the limits of what is possible. Webb is analyzing the faintest flickers of light, split into spectra, separated from the overwhelming glare of a distant star. Errors are possible. Calibration issues could trick us into seeing patterns where none exist. Scientists know this, and that's why they hesitate to declare victory. But even with caution, the anomalies stand out. Ammonia missing, methane and carbon dioxide in balance, DMS hovering at the edge of detectability. This is not the atmosphere of a dead planet. This is something else. What's more, K218b's star makes the case even more interesting. Red dwarfs are notorious for violent flares, bursts of radiation that can strip away atmospheres and sterilize planets. Yet K218b's atmosphere seems intact, stable, and balanced. How? Could its thick hydrogen layer be shielding the planet? Or could life itself be playing a role in maintaining stability, as it does on Earth? The idea that biology could regulate a planet's atmosphere isn't science fiction. It's, on Earth, the Gaia hypothesis suggests that life and the environment form a self-regulating system, each influencing the other to maintain habitability. If something similar is happening on K218b, then we're not just looking at the possibility of life, we're looking at the possibility of a living planet. Consider what this means for the search for extraterrestrial life. For decades, we've been told to look for biosignatures: oxygen, water vapor, methane, things that hint at biology. But the real power comes not from single molecules, but from combinations, from balances that defy chemistry alone. On Earth, the combination of oxygen and methane is a smoking gun for life. On K218b, the combination of methane, carbon dioxide, missing ammonia, and possible DMS may be the alien equivalent. It's not proof, but it's a fingerprint, one that says, this planet is not what you think it is. The implications ripple outward. If K218b is alive, it suggests that life is not rare, but common, not a fluke of Earth, but a natural consequence of chemistry given enough time. And if life thrives under a hydrogen-rich sky, in oceans hundreds of miles deep, then the galaxy is full of it. Suddenly, thousands of exoplanets once dismissed as uninhabitable become candidates. Hycean worlds, mini-Neptunes, strange sub-Earths, all could be alive. The odds of us being alone shrink to nothing. Yet for all the promise, the atmosphere of K218b remains a mystery. Why is ammonia gone? Why are methane and CO2 both abundant? Is DMS truly there, or is it a mirage in the data? Scientists are planning follow-up observations using Webb and other instruments. To sharpen the picture, each pass will refine the spectra, teasing out faint signals, clarifying whether what we're seeing is real or an artifact. But whatever the outcome, one thing is already clear. This is no ordinary planet. Its atmosphere is a puzzle, and puzzles like this don't come along often. Imagine what it must have felt like for the first scientists who saw those spectral lines, to realize that the faint dips and rises in light represented not just gases, but the possibility of biology. To know that you might be looking at the first evidence of life beyond Earth, carried across light years encoded in starlight. It is the kind of discovery that changes not just science, but philosophy, religion, and identity. For the first time, we might be glimpsing another biosphere, one utterly alien yet strangely familiar, breathing its secrets into the universe. The atmosphere of K218b is not just chemistry, it is a message. And whether it was written by volcanoes, oceans, or living cells, it demands to be read. The possibility that K218b harbors life is staggering enough. But once that door cracks open, another, even more haunting question slips through. If there is life there, could it be intelligent? For most of human history, we've imagined ourselves as the lone conscious beings in a vast, indifferent universe. But what if just 120 light-years away, beneath a hydrogen-rich sky and oceans deeper than mountains, are tall, there exists not just biology, but minds, beings capable of thought, memory, and awareness? And if such beings exist, then the next logical leap is even more unsettling. Could they already know about us? To answer that, let's start with something simple: time. For the past century, Earth has been broadcasting its presence into space, whether we meant to or not. Every radio transmission, every TV broadcast, every radar ping sent into the sky, those signals don't just vanish. They travel outward at the speed of light, carrying with them the unintentional story of our civilization. From jazz music of the 1920s to the moon landing of 1969, from presidential speeches to sitcoms, Earth's electromagnetic echo has been expanding into space for about 100. Today, that bubble of noise extends more than 100 light-years in every direction, brushing against the edges of star systems scattered across our galactic neighborhood. And among those stars sits K2. This means that right now, as we debate whether life could exist on that distant planet, the first century of our history has already arrived at its doorstep. If there are intelligent beings in those oceans, and if they have technology equal to or even ahead of ours, they could already be listening. They could be sifting through fragments of our broadcasts, trying to make sense of the static, catching glimpses of a species that only just began to dream of the stars. Think about the irony. We search for them with telescopes, while they might already be watching us through signals we sent carelessly, unaware we had an audience. But could intelligence really evolve in an environment like K218b's? At first glance, it seems impossible. No land, no fire, no metal. How could civilization rise in a world of endless ocean? We often think of intelligence as tied to tools, to hands that can shape stone and forge steel, but that may just be human bias. Intelligence doesn't need to look like us. It doesn't need cities, skyscrapers, or spacecraft to exist. On Earth, dolphins, whales, and octopuses demonstrate remarkable intelligence without ever building anything permanent. They communicate, cooperate, solve problems, and even show signs of self-awareness. And all of that is achieved underwater, without fire, without industry, without the trappings of human progress. Now imagine an ocean far larger, older, and more stable than Earth's, where life has had billions of years to evolve without interruption. In such a cradle, intelligence might not just appear, it might flourish. The forms it could take defy imagination. Perhaps beings with bodies adapted to crushing pressure, luminous creatures using bioluminescence to communicate across the dark. Perhaps collectives of smaller organisms that form networks of thought, intelligence spread across schools or swarms rather than individuals. Intelligence may not look like a brain, it may look like a web, a chorus, a pattern. In an environment so different from our own, we have no reason to think evolution would converge on something like us. It could be stranger, more alien than anything our fiction has conjured, and yet intelligence is not defined by shape but by function. The ability to adapt, to imagine, to ask questions. If that capacity exists beneath K218b's waves, then we are not the only minds in the cosmos. And here's where the unease begins. If they are there, if they are intelligent, they may already know we exist. Our signals, though faint, could be detectable with technology just a bit more advanced than ours. To us, those signals are lost in cosmic noise, but to a civilization accustomed to interpreting faint chemical signatures across stars, the same way we've spotted dimethyl sulfide in their atmosphere, our broadcasts might be as clear as a beacon. Imagine their scientists pointing instruments at Earth, catching snippets of music, of speeches, of drama. Imagine the shock of realizing that they are not alone, that across the void another species has awakened, sending its voice into the dark. For us, K218b is a mystery. For them, Earth might already be a revelation. But what would they think of us? Would they see us as dangerous, violent creatures, our history full of wars, conflicts, and destruction? Would they dismiss us as primitive, a species barely crawling into technology, not worth their attention? Or would they see in us something familiar, beings struggling to understand the universe, reaching beyond their world in curiosity and hope? The truth is, we can't know. The knowledge that someone might already be listening, might already be judging, is enough to send a shiver down the spine. There's another unsettling layer. K218b's oceans may conceal their civilization in ways that make them invisible to us. While we send probes into space and build telescopes to peer outward, they might be turned inward, focused on their endless seas. Their intelligence may not seek the stars, not because they lack the capacity, but because they lack the need. To them, the cosmos may be irrelevant, a distant abstraction compared to the richness of their ocean. Yet by accident, by curiosity, by sheer chance, they might still notice us, catching our signals like fishermen catching strange driftwood washed in from another world. They might see us long before we ever see them. This asymmetry is haunting. We imagine first contact as a moment we initiate, a spacecraft landing, a message sent. But what if first contact has already happened? Not with us discovering them, but with them quietly discovering us. What if we are already part of their knowledge, an entry in their equivalent of an astronomy journal, species catalogued and filed away as young, noisy, and unstable? It is a reversal of roles that challenges our sense of importance. We think we are the observers, the searchers, the ones in control. But perhaps we are already the observed, the discovered, the mystery in someone else's sky. And here lies the paradox. We crave discovery, yet we fear being discovered. For decades, scientists have debated the risks of broadcasting our presence to the stars. Some argue we should send messages, announce ourselves boldly, show that we are here. Others warn that silence is safer, that to shout into the void is to invite dangers we cannot predict. But the truth may be that the decision was made long ago, by building radio towers, by sending television signals, by bouncing radar off the moon. We have already spoken. The message has already gone out, and if K218b is alive with intelligence, then our introduction has already been delivered. So we stand at a crossroads. The signs from K218b's atmosphere suggest life. The silence from the stars suggests caution, and between the two lies a possibility we are only beginning to consider, that not only are we not alone, but that someone else may already know us, watching silently from across the abyss. Whether they will ever answer, or whether they already have in ways we don't yet understand, remains the greatest question of all. Because in the end, the search for intelligence on K218b is not just about them, it is about us, about how we see ourselves, how we define life, and how we imagine our place in a universe that suddenly feels much more crowded. If we are not the only minds in existence, then everything changes. We are no longer the center of the story. We are one chapter among many, part of a cosmic community we have only just realized exists, and that realization may be the most profound discovery in human history. Not just that life exists, but that we are already part of something far bigger, something that has been listening all along. For as long as humanity has looked up at the stars, we've wondered if something out there is looking back. But until recently, our tools were simply too crude, too limited, too bound by distance to answer. The night sky dazzles with light, yet every pinprick of brightness overwhelms the tiny, fragile signals we need most. The faint glow of planets hidden in the glare of their suns, carrying the chemical fingerprints of whatever exists in their skies. For centuries, those worlds were invisible to us, more dream than data. That began to change in the 1990s, when astronomers first detected exoplanets, not by seeing them directly, but by noticing the tiny wobbles they caused in their stars. Suddenly, the universe became crowded with possibilities, but we still couldn't see enough. We could detect planets, measure their orbits, guess at their sizes, but not their atmospheres, not their chemistry, not their secret. And then came the James Webb Space Telescope, a machine so powerful it has already rewritten astronomy in just a handful of years. Unlike any instrument before it, Webb was designed to see the invisible. It doesn't peer primarily in visible light, the narrow slice of the spectrum our eyes can see, but in infrared. That's where the universe whispers its oldest and faintest secret. Starlight stretched by distance and time, heat signatures from planets, the subtle fingerprints of molecules, all of it glows in infrared. From Earth's surface, that light is impossible to study, blocked by our own atmosphere. That's why Webb had to be launched into space, carried to a stable orbit 1 million miles away, far beyond the interference of Earth's air and heat. Out there, shielded by its enormous golden mirrors and tennis court-sized sun shield, it stares into the dark with sensitivity so extreme it can pick up the warmth of a bumblebee on the moon. But Webb's brilliance isn't just in seeing faint heat, it's in breaking light apart. When starlight filters through the atmosphere of a planet during a transit, the gases in that atmosphere absorb certain wavelengths, leaving tiny gaps, dips, or fingerprints in the spectrum of light. By capturing and analyzing those fingerprints, Webb can tell what a planet's air is made of, even from hundreds of light years away. It's a technique known as transmission spectroscopy, and it is as close to magic as science has ever come. Imagine being able to shine a flashlight through a glass of water and not only confirm it's water, but determine if there's sugar, salt, or bacteria inside. Webb is doing that, not with a glass, but with entire planets orbiting stars across the galaxy. This is how we learn that K218b carries water vapor, methane, carbon dioxide, and perhaps even dimethyl sulfide. It's how we discovered the strange absence of ammonia, a clue that chemistry there may not follow lifeless expectations. None of this would have been possible with the Hubble telescope, or even with ground-based observatories. Webb's instruments are so sensitive they can detect the equivalent of a single molecule in a vast ocean of gas, passing details finer than the width of a human hair in the spectrum of starlight. For the first time, we are not just seeing planets as points of light. We are dissecting their atmospheres, listening to the chemical music they play as they orbit their stars. What makes Webb's achievement even more remarkable is its ability to suppress starlight. Stars are blindingly bright compared to the planets that orbit them, like floodlights drowning out fireflies. To see the planets at all, Webb uses techniques like coronagraphy, which blocks the overwhelming glare of the star, allowing the planet's faint signal to emerge. Think about the scale of this. K218b is orbiting a star more than 100. From our vantage point, that distance shrinks the separation between star and planet to less than a fraction of an arc-second, and yet Webb can isolate the planet's signal, filter it, and analyze the gases in its air. It's like standing in New York City and being able to tell what perfume someone is wearing in Los Angeles just by studying the faintest flicker of light. And this is just the beginning. Webb has already shown us galaxies formed in the first 100 million years after the Big Bang, revealed stars in the act of being born, and mapped out planets like K218b with unprecedented clarity. Each discovery stretches the boundary of what we thought possible, but perhaps its greatest gift is this. It has transformed the search for life from a question of philosophy to one of observation. For the first time, we can look at a planet and say with evidence, this is what its atmosphere holds. This is how it behaves. This is what it might mean. It moves the search from speculation to science. The implications are profound. With Webb's capabilities, we no longer have to wonder if Earth is unique. We can test it. Already dozens of exoplanets have been flagged for study, many in their stars' habitable zones, many showing tantalizing hints of water, clouds, or unusual chemistry. In the coming years, Webb will dissect them one by one, building a library of alien worlds, each with its own chemical signature, each offering new clues to the puzzle of life. And as that library grows, patterns may emerge. We may find that methane and carbon dioxide coexist on many planets. We may find that water vapor is common, that dimethyl sulfide or some alien equivalent appears more often than chance allows. We may discover that life is not a rare miracle, but a cosmic inevitability. But there's another layer to this story. Webb is not alone. Already its discoveries are paving the way for the next generation of telescopes, both space-based and ground-based, that will push the search even further. Missions like the Nancy Grace Roman Space Telescope, or giant Earth-based observatories like the extremely large telescope in Chile, will build on Webb's work, probing atmospheres with even greater precision, even attempting to image planets directly. In a sense, Webb is the trailblazer, the scout sent ahead to show us what's possible, and what it has shown us already changes everything, that the universe is full of voices, chemical signals waiting to be heard, planets waiting to be understood. For now, K218b is the most compelling case. It is the first planet where the chemistry points so strongly toward biology, where the absence of ammonia and the presence of methane, carbon dioxide, and dimethyl sulfide combine into a mystery that demands explanation. But it will not be the last. Every time Webb peers into the light of another world, we edge closer to the day when doubt ends and confirmation begins. The day we no longer ask if life exists elsewhere, but what kind, how much, and how different from us it may be. The James Webb Space Telescope is more than an observatory. It is a time machine, a microscope, a translator of the universe's faintest whispers. It has taken a question humanity has asked since its beginning. Are we alone? And given us a way to find out. For the first time, the answer no longer lies in faith, myth, or speculation. It lies in data, in light, in spectra carved from the silence of space. And as we look at K218b and wonder what lies beneath its clouds, we do so not as dreamers, but as scientists, armed with the tools to finally uncover the truth. For centuries, Earth felt like a miracle, an improbable oasis in a vast desert of stars. The odds of life, let alone intelligent life, seemed so small that many scientists once argued it was foolish to expect it anywhere else. But discoveries over the past 30 years have flipped that thinking upside down. Instead of being rare, planets are everywhere. Instead of being exceptions, Earth-like conditions might be the rule. And K218b, as remarkable as it is, may not even be the strangest or the most promising. It is simply the one that caught our attention first, one where chemistry revealed its secrets under the gaze of the James Webb Space Telescope. The more we look, the clearer it becomes. If K218b shows hints of life, then it may be just the beginning. Astronomers now know that there are more planets in our galaxy than stars, billions upon billions of them, scattered across the spiral arms like cosmic seeds. Among those, a surprising fraction fall into categories once thought uninhabitable. Hycean worlds like K218b, super-Earths with thick atmospheres, rocky planets around dim red dwarfs. These classes of planets outnumber Earth-sized Sun-like pairings many times over. If even a small percentage carry oceans, atmospheres, and the right chemistry, then the galaxy could be overflowing with habitable environments. K218b, in that sense, is not a miracle. It is a clue, a signal that the odds of life are stacked in favor of abundance, not scarcity. Already, other exoplanets are joining the list of intriguing candidates. Take TRAPPIST-1, a system only 40 light-years away, with 7 Earth-sized planets orbiting a cool red dwarf. Several of those worlds sit in the so-called habitable zone, where temperatures could allow liquid water. Observations with Hubble and now Webb are beginning to probe their atmospheres, searching for the same kinds of signals we saw with K218b. The early results are complicated. Some appear stripped bare by their stars' flares, others remain shrouded in mystery, but the very fact that multiple potentially habitable planets orbit a single nearby star is astonishing. In one system, we may have a laboratory of possibilities, each world offering a different outcome for life's chances. Then there is LHS 1140b, a super-Earth orbiting a red dwarf about 48 light-years away. Larger than Earth but smaller than Neptune, it falls into the same sub-Neptune category as K218b, and some studies suggest it may host a dense atmosphere and liquid water. Early data hinted at clouds or haze in its skies, raising the possibility of a climate capable of supporting biology. Like K218b, it may be an ocean world, with water covering much of its surface. If Webb turns its attention fully to this planet, we could see a repeat of the same mysteries: methane, carbon dioxide, missing ammonia, or even stranger signatures. And these are just the nearby candidates. Kepler-22b, discovered over a decade ago, was one of the first planets confirmed to orbit in its star's habitable zone. Since then, Kepler and other surveys have revealed thousands more, from small rocky worlds to super-Earths with thick skies. Some orbit stars stable enough to provide billions of years of steady light. Some orbit dim dwarfs where conditions may be harsher, but still survivable. In system after system, the pattern repeats: planets with potential, waiting for our instruments to peel back their atmospheres and reveal their truths. The most remarkable part is not that K218b shows signs of life, it's that we found it so quickly. Webb has only just begun its mission, only just pointed at a handful of promising candidates. If in its first years it has already uncovered tantalizing biosignatures, what will it find in the next decade? The sheer speed of discovery suggests that biosignatures are not rare gems, but common threads woven through the galaxy. If the first ocean world we examined hints at life, then logic suggests there are countless more. We didn't stumble upon a 1 in a billion miracle. We tapped into a pattern. This raises a radical possibility that life in the universe is not only common, but inevitable. Given the right conditions, liquid water, energy, time, chemistry seems to tip naturally into biology. On Earth, life appeared quickly after the planet cooled, within a few 100 million years. It wasn't a fragile accident, it was a natural consequence of the environment. If the same processes operate across the galaxy, then wherever oceans exist, life may follow. And with billions of oceans scattered across billions of planets, the odds shift from unlikely to overwhelming. Life is not rare. Life is the rule. Of course, skeptics caution patience. Finding methane and carbon dioxide or even dimethyl sulfide doesn't prove biology. Geological processes could mimic life's chemistry. Strange exotic reactions could create gases we don't yet understand. But that argument begins to crumble when patterns repeat. One anomaly can be dismissed. 10 anomalies, spread across multiple planets, begin to form evidence. 1,000 anomalies, all pointing toward biology, become proof. K218b is the first whisper. The others will follow, building into a chorus the universe can no longer deny. And there's something poetic in this unfolding picture. For generations we told ourselves that Earth was unique, a fragile blue dot in an ocean of nothingness. But the more we look, the more we see that the cosmos is not barren. It is fertile. Worlds like K218b, LHS 1140b, TRAPPIST-1's planets, Kepler's endless catalogue, they are not exceptions. They are the fabric of reality. Each one may hold its own oceans, its own atmospheres, its own struggles and triumphs of chemistry and biology. Each one may be alive in ways we cannot yet imagine. And yet, Each discovery brings a deeper challenge. If life is common, why don't we see it? Why is the universe not already full of signals, transmissions and civilizations spanning the stars? This is the paradox first raised by physicist Enrico Fermi. If life is common, where is everybody? K218b and its cousins suggest that the conditions for life are plentiful. If that's true, then civilizations may have risen countless times, but perhaps they are hidden beneath oceans, bound to their worlds, never broadcasting. Perhaps they are there but silent, choosing not to reveal themselves. Or perhaps, chillingly, intelligence is fragile, rising and falling quickly, leaving behind only the quiet chemistry of biology. K218b shows us that life may not be rare. Other planets confirm that habitability may be everywhere. Together they transform the way we see ourselves. We are no longer a lonely miracle. We are one among many, part of a universe alive with possibility. And as Webb and its successors continue to peel back the skies of these distant worlds, we may soon learn that our question, "Are we alone?" was the wrong one all along. The real question is not whether life exists elsewhere, but how many kinds of life exist, how many worlds harbor it, and how strange, how alien, how beautiful those forms of life may be. Because if K218b is alive, then the galaxy is alive. And if the galaxy is alive, then we are not just inhabitants of Earth, we are citizens of a cosmic ocean, one teeming with worlds, each with its own secrets, waiting for us to listen. For every hint we gather that the universe may be teeming with life, there is one overwhelming silence that weighs against it: the absence of signals. If biology is common, if planets like K218b are alive, and if evolution naturally gives rise to intelligence, then by now the galaxy should be buzzing with activity. With billions of stars older than the Sun, many with habitable planets, civilizations could have risen millions of years before humanity even lit its first fire. They would have had time not only to develop radio, not only to explore space, but to cross the galaxy itself. If life is everywhere, intelligence should be everywhere, and yet we look into the dark and hear nothing. This is the riddle known as the Fermi paradox, and K218b's strange chemistry throws it into sharper focus than ever before. Enrico Fermi posed the paradox in a casual conversation in 1950, asking simply, "Where is everybody?" Since then, scientists, philosophers, and dreamers have struggled with its implications. The paradox rests on three premises. First, that the galaxy is vast and old, with more than enough time for civilizations to emerge. Second, that interstellar travel, while difficult, is not impossible, given that stars are separated by relatively short distances on cosmic scales. And third, that intelligent life, once it appears, has a tendency to expand, explore, and leave traces of its existence. If all of this is true, then even one civilization rising early in the galaxy's history could have spread across it by now. But instead of a galaxy lit with their beacons, we see only stars, planets, and silence. There are many possible answers, none of them comforting. Some argue that life is far rarer than we think, that K218b is a false alarm, that Earth is a staggering fluke, that biology almost never gets started. But that explanation grows weaker with every new discovery. The universe is not shy about making planets, oceans, and atmospheres, and with signs of potential biosignatures already appearing in Webb's early observations, it seems harder to argue that life is rare. If K218b, the first Haitian world we examined closely, already shows hints of life, then the odds suggest biology is common, perhaps even inevitable. So the paradox deepens. If life is everywhere, why isn't intelligence? One answer is that intelligence is fragile, that civilizations are self-limiting. Perhaps biology thrives, but intelligence destroys itself before it can spread. On Earth, we see both the promise and the peril in less than 2 centuries. We've gone from horse-drawn carriages to nuclear weapons and climate change. Our technologies are powerful, but they carry risks we may not survive. If other civilizations face the same traps, self-destruction, environmental collapse, warfare, then most may vanish long before they become galactic explorers. In that case, K218b may be alive, but silent, hosting oceans full of microbes or even animals, but never civilizations that build telescopes or send signal. Another possibility is that intelligence arises often, but chooses silence. Imagine a galaxy where civilizations exist but remain hidden, either by choice or by necessity. Perhaps they fear attracting predators, advanced civilizations that consume or destroy others, or perhaps they follow a principle of non-interference, listening to young species like ours without revealing themselves, the way we might observe animals in the wild without disrupting them. If so, then K218b's oceans could harbor intelligent beings who already know of us, already study our signals, but deliberately remain quiet, waiting for us to mature before making contact. The silence, then, is not absence. It is restraint. A third answer is that intelligence is simply different from what we imagine. We look for radio signals, for beacons for technologies like ours, but what if alien intelligence doesn't communicate that way? On Earth, whales and dolphins use sound in ways we still barely understand. Octopuses communicate with color and movement, and even trees share signals through networks of roots and fungi. Intelligence doesn't have to be technological. It doesn't have to build rockets or broadcast radio. It could exist in forms we cannot detect, in patterns we don't yet know to look for. K218b's oceans may be alive with intelligence that expresses itself in light, chemistry, or collective behavior, invisible to us but as real as our own. The silence, then, is not emptiness. It is our deafness. There is also the unsettling idea that civilizations do expand, but their timelines are so short compared to cosmic time that they miss each other. Imagine a civilization rising, spreading to nearby stars, and then vanishing through collapse, transformation or transcendence before another arises. The galaxy could be full of ruins of abandoned technologies, of echoes from civilizations long gone. If so, then K218b may not be the home of a current intelligence, but perhaps of one that rose and fell millions of years ago, leaving only the quiet work of biology in its oceans as the last trace of its existence. The silence in this case is a grave, but perhaps the most haunting explanation is that the silence is temporary, that we are simply early, and the universe is only now awakening. If life arises easily, but intelligence takes longer, then perhaps most civilizations are still in their infancy, just as we are. In that case, K218b's strange chemistry may be the first sign not just of alien biology, but of the beginning of a galactic awakening. We may be standing on the threshold of a new era, one in which the silence begins to break. Not with one signal, but with many, as young civilizations reach out at the same time, discovering one another in a sudden explosion of connection. Whichever answer is correct, K218b is a turning point. If its biosignatures hold up under scrutiny, then life is not rare, and if life is not rare, then the Fermi paradox cannot be ignored. We must confront the silence not as absence, but as mystery. Are we fragile, doomed to destroy ourselves like so many others? Are we young, too early to hear the chorus? Are we deaf, looking for the wrong signs? Or are we watched, studied in silence by beings who prefer to remain hidden? Each possibility is unsettling. Each reshapes how we see ourselves. And yet, there is hope in this paradox. The silence is not a wall, it is an invitation. It challenges us to look harder, to listen differently, to expand our understanding of what life and intelligence can be. The discovery of planets like K218b forces us to confront the paradox head-on, to accept that life may be everywhere, that intelligence may be strange, and that the universe is far richer than our imaginations have allowed. It pushes us not toward despair, but toward humility, toward the recognition that we are not the measure of all things, but one thread in a tapestry far larger than ourselves. Perhaps in the end, the silence is not a failure, but a gift. If the universe is alive but quiet, then it gives us time to grow, to mature, to learn how to listen. Time to prepare for the day when the silence ends, not with a whisper, but with a chorus. And maybe, just maybe, K218b is the first note of that chorus. A faint signal carried in its atmosphere, waiting for us to hear it. The idea of first contact has always lived somewhere between science and myth, between the realm of speculation and the dream of confirmation. For decades, books and films have imagined it, the moment when we look up into the sky and realize we are no longer alone. But if K218b's strange signals turn out to be more than chemistry, if they are whispers of biology, or even of intelligence, the thought experiment suddenly shifts into a practical question. What happens if they know about us? What happens if they decide to answer? And, most importantly, what happens if we decide to answer back? First contact, for all its wonder, carries risks that few are prepared to confront. The first danger lies in our eagerness. Humans are storytellers, explorers, driven by curiosity and the desire for connection. When we find a mystery, our instinct is to reach out, to solve it, to communicate. If K218b or another world sends even the faintest signal, the temptation will be overwhelming to respond immediately, to announce ourselves, to extend a hand across the stars. But this impulse could be reckless. We know nothing about the beings on the other side, nothing about their values, their intentions, or their capacity for harm. To broadcast our presence openly, without caution, would be like shouting our address into the dark of a forest without knowing who or what might be listening. It is not paranoia to consider this. It is prudence. On Earth, first contact between civilizations has often led to disaster, especially for the less technologically advanced side. Why should the cosmos be different? Yet silence carries dangers of its own. If life on K218b is intelligent, it may already be listening to us, already aware of our existence through the radio waves we've been leaking for a century. In that case, the question is not whether to hide, but how to respond, to ignore them, to retreat into silence after decades of broadcasting unintentionally, might send its own kind of message, a message of fear, of disinterest, or even of hostility. And if we are dealing with a civilization advanced enough to decode our signals, they may already be judging us, not by what we choose to say now, but by what we've already said unknowingly. Our wars, our music, our debates, our chaos. The risk then is not just in speaking, but in having spoken without meaning to. We are already exposed. This creates a paradox of communication. To respond may invite danger, to remain silent may convey the wrong message. And within that paradox lies an even deeper problem. Who speaks for Earth? Who has the authority to answer if K218b or any other world sends a signal? Governments? Scientists? The United Nations? Humanity has never faced a decision that affects not just one nation, but all of us, all at once. A single message, a single misstep, could define how another intelligence perceives us for millennia. The weight of that responsibility is staggering. Some scientists argue that we should prepare now, crafting a global protocol for contact. We should decide what to say, what not to say, and who has the right to send the word. Others believe the safest course is silence, that the risks are too great, that we should listen but never speak, learning all we can without revealing anything more. Both positions have merit, and both reveal the immensity of the unknown. Silence keeps us safe but alert. Speech risks connection and catastrophe in equal measure. The truth is, no one knows which path is right, and beyond the practical lies the psychological. What does first contact do to us? Even without a signal, the mere possibility that K218b's atmosphere contains the fingerprints of life has already unsettled how we see ourselves. Imagine the impact of undeniable proof. Religions would be shaken, philosophies rewritten, identities reshaped. Nations might scramble to claim ownership of the discovery, to weaponize it, to control the narrative. Fear could spread as quickly as wonder. Some might see alien life as a threat, others as saviors, others still as an irrelevance. The world would fracture in its response, and all of this could happen before we even understand what those beings are, or whether they exist at all. There is also the question of scale. Contact does not have to mean conversation. It could mean something as subtle as detecting an artificial chemical in K218b's air, something that could not exist without technology. It could mean spotting a structure in orbit, or strange signals that do not fit the patterns of nature. Each of these would be contact of a kind, not direct, but undeniable. In those cases, we would not be speaking to them. We would be observing them, and that observation alone might be enough to change everything. Would we treat them as equals? As curiosities? As threats? Would we even be able to comprehend what we were seeing? But what if contact is direct? What if a message is sent, not a whisper of chemistry but a deliberate signal? Mathematics, language, music. Then the responsibility deepens. To respond would mean creating a bridge between two species, separated by oceans of distance and perhaps by oceans of thought. Communication would be slow, limited by the speed of light. A message to K218b would take 220 years to arrive. A response would take another 120. Any conversation would span centuries, longer than nations survive, longer than most human institutions last. To commit to that exchange would be to commit for generations, to tie humanity's story to theirs, in a dialogue that outlives us all. Are we ready for that? Are we even capable of it? And what if the signal is not friendly? Not an invitation, but a warning, or worse, a threat? The universe is vast, and while life may be common, kindness may not be. A civilization advanced enough to send signals across light years is advanced enough to destroy or dominate us if it chooses. The gulf of distance gives us comfort, but technology may close that gulf in ways we cannot predict. To assume benevolence is dangerous. To assume hostility may be just as limiting. The truth is, we would be dealing with the unknown, and the unknown is dangerous by definition. In the face of all this, one thing becomes clear. First contact is not just a scientific question. It is a moral one, a political one, a philosophical one. It forces us to ask who we are, what we value, and how we present ourselves to the cosmos. Do we present ourselves as explorers, eager to connect, as warriors, ready to defend, as caretakers, cautious and humble? Or do we choose silence, letting our existence be known only by the accidental leakage of our signals, hoping that curiosity does not one day bring someone knocking at our door? K218b is not yet sending us messages. It is not yet broadcasting its presence deliberately, but in its chemistry, in its atmosphere, in the whispers Webb has caught. It has already forced us to confront these questions. It has already made us think about the possibility of others, about the responsibility of connection, about the risks of being known. It has already begun the conversation, even if the other side has yet to speak, and that may be the greatest danger of all, that the first contact is not an exchange of words, but an exchange of thoughts within ourselves, a recognition that we are not alone, and that our choices now will shape how we meet the universe when it finally answers back. The search for life beyond Earth has always carried with it equal measures of hope and fear. For centuries we asked the question as if it were abstract, philosophical, something to debate, rather than something to answer. But now, with planets like K218b under the lens of instruments powerful enough to peel back their skies, the question is no longer philosophy. It is science. The faint fingerprints of chemistry drifting through that alien atmosphere are not just lines on a spectrum. They are messages, whispers from across the cosmos, telling us that Earth is not exceptional, that life may not be rare, and that the universe itself may be richer and stranger than we ever dared to believe. And yet, with every discovery we are reminded of our smallness. K218b is 120 light-years away, impossibly far by human standards. If we wanted to send a message today, we would not live to see the reply. If we wanted to visit, it would take technology we do not yet possess. Perhaps centuries from now, the very act of studying it, of inferring oceans and molecules from starlight, is a reminder that we are still infants in the cosmic scale, peering from the cradle into a universe that dwarfs us. But in as infants, we are beginning to see, and what we see suggests we are not alone. The implications ripple outward. If life thrives on K218b, it may thrive on countless other worlds, scattered through the galaxy like sparks in a dark ocean. If intelligence has risen elsewhere, then the silence we hear is not absence, but a mystery waiting to be solved. And if we are among the first to awaken, then we carry a responsibility unlike any before, to choose how we reach out, how we present ourselves, and how we prepare for the day when the silence ends. The answers we choose will define not just our generation, but all who come after. Perhaps that is the true gift of K218b, not proof, not certainty, but perspective. It reminds us that we are part of a vast, interconnected story, one in which Earth is not the stage, but a stage, not the miracle, but one of many. It forces us to confront questions bigger than science. What kind of species are we? What kind of neighbors will we be? Do we embrace the possibility of others with humility, curiosity, and care? Or do we let fear and recklessness shape our choices? The universe is watching not because it is alive, but because we are, and what we do next will echo outward across space and time. In the end, the discovery of K218b's secrets is less about them and more about us. It is about courage to look beyond our own world, our ability to listen to faint whispers in the dark, and our willingness to accept that the story of life is bigger than Earth alone. Whether K218b is truly alive or whether it is a false alarm, it has already changed us. It has shown us that the universe is full of possibilities, and that the answers are within reach if we dare to keep searching. And that may be the most profound discovery of all, that in looking for others we have found ourselves standing on the threshold of a universe that is vast, alive, and waiting.